So in the previous video, we sort of go through some of the concepts. We talk about electric potential energy and how we can imagine it to be like a compressed spring for like charges kind of cases, or for a stretched spring for kind of opposite charges kind of cases. So we know that because we think of a pair of charges to be something like a spring, therefore they will store electric potential energy. Then we move on to relate this concept of electric potential energy. We relate it to work done. We see that if it's work done, it can be related to the change of potential energy. We use what we learned from last semester when we talk about work, energy, and power. We relate what we have learned from last semester to what we are going to learn this semester and say that the work done by electric force is equals to negative delta U, and work done by external is equals to delta U. So this is what we have learned until this point. But what I'm going to do right now is I'm going to take this concept that we have just learned, in which work elect is equals to negative delta U and work external is equals to delta U. I'm going to take this concept here and merge it to this particular definition which I have stated here. I've stated this definition in the first part of the video, but I don't really explain it that much. So here I'm going to really go and expand this particular definition so that we can understand this definition more mathematically. Okay, so here I'm going back to the definition. Okay, so right now I'm back. This one title should be in green. I need to be a bit more consistent. Okay, back to the definition. Of electric potential energy. Okay, so this is the definition of electric potential energy that we just mentioned in the first part of the video. So I'm going to pop it up here. So this is the definition. Okay, so let me write this as definition. Okay, if you read the definition being given here, you can see that it mentions work required. Okay, so this work required here is definitely referring to work done by the external force. Okay, if it's mentioned, if it's work done by the electric force, they have to mention explicitly the word work done by electric force, or they need to mention work done by electric field, or they need to mention work done by electric charge, but they don't mention any of this, and they say the word required. So we know from our discussion earlier in the first part of the video, we know that this one is referring to work done by external force. Okay, and now we are going to bring a charge from infinity to a specific point. Okay, initially it is at infinity, then it will be at a specific point. So we know that initially, we can say something like initially it is at infinity, then afterwards he's going to move towards a direction, move towards a point which is at a certain distance of r. Okay, I'm just going to call it by r. Okay, so you move from somewhere infinity to a distance of r in the system. Okay, so based on this equation right now, with the knowledge that we have learned just now about work done, we can actually try to work on something with it. Okay, we know that we are going to analyze it using work done by external force, and we know that this is a journey from initial position which is at infinity to a final position which has a distance r certain somewhere. Okay, so we know that work done by external force is equals to delta U, so we can change it to become delta U, and we can further expand it to become U final minus U initial. And because all of you know that our final position is at the point r, at the distance of r away from a certain somewhere, we can write it as UR. Whereas the initial position is at infinity, so I can write it as infinity. Okay, so I'm just expanding the equation that we have learned from just now based on the definition that we have over here. Okay, but here I'm going to add on some important information over here. I'm going to say that at infinity, this is what we have defined, and what the whole wide world have already come to agreement on, is that, and we agree that at infinity, we are going to set the electric potential energy to be equal to 0. Okay, so I hope you all can still remember something from last semester. I'm going to briefly mention it. But do you remember that when we talk about gravitational potential energy, there's such thing called a reference height? A place, a certain altitude which we set height is equal to 0, or we call it as reference position, a certain level which we are going to call it as height is equal to 0. So at that point, the gravitational potential energy is equal to 0. If you go higher than that position, you have positive gravitational potential energy. If you go lower than that position, you have a negative gravitational potential energy. That's what we learned last semester. Okay, but the idea I want to tell you right now is for any kind of potential energy, we have to sort of set where we want the U to be equal to 0. For gravitational potential energy, we usually set the ground as equal to 0, or for elastic potential energy, we usually set when the spring is unstretched or uncompressed, when it's at its original length, we usually set it as U is equal to 0. Okay, but we have to sort of set a kind of reference position. And in this particular case, infinity is our reference position. Okay, so because the potential energy is equal to 0 at this position, therefore we can sort of make a statement and say that U infinity over here be equal to 0. Therefore, we are only left with UR. Okay, it seems like a very pedantic kind of expansion over here. I'm expanding delta U, then I'm crossing out one of the U to become equal to 0, but at the end I get UR. But the purpose of me showing this is I just want to tell you that this definition here is true, because if I expand the definition mathematically, if I take this definition and I expand it mathematically, I'm able to prove that the result of my expansion actually refer directly to electric potential energy. Okay, if this definition is not true, I expand it, I'll get something else. I will not get U as the final result. But as you can see here, if I expand it faithfully based on the equation, and based on the definition over here, if I expand it faithfully, I'll get the result of U. So that means that this definition here is actually really representing electric potential energy. Because what I get as a result of expanding this definition, I get U, which is electric potential energy, as the result. Okay, so just now we have actually learned there's another equation for work done, right? There's also the work done by electric version as well. So let's write it down. If we choose to discuss this situation using work done by electric, and we move from infinity to a certain specific position R, if we choose to analyze it using work done by electric, I believe you'll notice that there will be something wrong with it, because this equation has a negative sign. So if you expand it, there will be a negative in the equation, and you know that this is U final is UR, U initial is just U infinity. So with the help of U infinity being 0, you cross out this, and at the end you still get an answer which is not exactly equals to U. Okay, so that means if we just say that electric potential energy is a work done by electric force to bring a charge from infinity to a specific point, that is not the true definition. Because if you say work done by electric force to bring a charge from infinity to a specific point R, if you expand it, you get something looks like an electric potential but with a negative sign in front. So that means that this, if you write as work done by electric force, is incorrect. But if you choose to add on a negative in front over here, so that means you're going to bracket this thing with a negative in front. Now that makes a different story. So with a negative in front, your equation right now will change to be exactly UR. Your negative work done by electric force to bring a charge from infinity to R will now be equals to UR. So that means if we want to describe the definition in terms of work done by electric, you have to add on a negative sign in front. That means we can actually re-represent the definition in another way. So we can write another definition, and that another definition for electric potential energy is It's the negative of the work done by electric force to bring a charge from infinity to a specific point. I believe you see that the rest are the same, right? In the electric field. Okay, I'm just going to write it here in the electric field. Sorry for the mismanagement of space. Okay, so what I've changed here is, instead of writing it as the work required, I've changed it to become the negative of the work done by electric force. So this is also a valid definition, because the negative of the work done by electric force is actually the same thing as the work done by external force. Okay, so this is also seen in certain books somewhere. This is also an acceptable definition. This is also an acceptable definition. Okay, there's many ways to twist around the definition. You can actually move from a specific point to infinity. That is a negative of the work required. You move from a specific point to infinity, then it's a positive for the work done by electric force. You can spin in many ways, but that's not the point of our discussion. I'm just telling you that it can be flexible, but you can figure it out on your own actually. Okay, so what I'm trying to prove to you here is that the definition here is true. It's actually representing electric potential energy. Okay, but we are not going to stop there actually. We are actually going to take this definition a bit more seriously. Okay, so how do we take this definition a bit more seriously is we are going to try and derive the equation for electric potential energy using the definition that we have. Okay, so what are we going to do now is we are going to derive equation of electric potential energy based on the definition. Okay, so our definitions say that the charge will be moved from somewhere which is infinity to another somewhere which is at a specific point in the electric field. So that means that initially your charge is somewhere very, very far away. Okay, so let's say your system right now, your default system has a Q, has a charge Q over here. Okay, but Q is not our focus. Let's say we are focusing on what charge do you want to focus on? Let's say we are focusing on, let's use a striking color. Green is striking maybe. Okay, we have a charge Q which is initially very, very far away from Q. Okay, the distance here is infinity. Okay, so we want to bring this particular charge Q from infinity, which is somewhere very far away from this system over here. We are going to bring it near to this charge Q so that it is in the electric field produced by charge Q. Okay, we bring this charge Q from somewhere super, super far away, which cannot sense any electric field produced by Q. We are going to bring it nearer to charge Q so that it can, to charge big Q, so that this charge small q here is in the electric field produced by charge big Q. Okay, so I think I should probably exaggerate a bit the Q. Okay, it seems a bit too near here. Let's maybe make it somewhere even further, somewhere here maybe. Okay, initially it's somewhere there. So super, super far away. So I'm going to use the arrow to be somewhere that is so far away that it is dot 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 dot. And this is a line. And if you extend it until somewhere dot 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 super, super far away, you find that the charge that we are interested in, Q over here. Okay, initially Q is very, very far away from the system, but what happened is we are going to bring the charge near. So let's say the charge is undergoing some kind of motion from somewhere super, super far away and is being moved somewhere over here. Okay, so finally we'll see the system to be something like this. Final, the charge Q remain at its own place. Okay, we are not focusing on charge big Q, we are focusing on charge small q here. And charge small q right now has moved to this position over here. And this position here, we can measure the distance from the charge big Q, and the distance is R. Okay, so I'm just visualizing the situation being mentioned over here. What does it mean by from infinity to R? Okay, so infinity to R means by initially very, very far away, but bring it to a distance of R away from from a certain charge, something like that. Okay, so this is a situation that we are going to study because this is a definition given to us. And based on electric potential energy's definition, we are going to use the bottom definition over here. We know that if we want to find the electric potential energy over here, we have to follow the definition. So what is the EPE stored here? We want to find out the equation to represent the EPE being stored here. Okay, so to find that out, we have to look at the definition. The definition says that electric potential energy, W, is equals to the negative, the electric potential energy U, sorry, I'm messing this up. Okay, the electric potential energy U is the negative of the work done by electric force, so work elect, to bring the charge from infinity, so initially is at infinity, to a specific point in the electric field. So this is to R. So this is what we will get. If we go and look at the definition faithfully, we see that U is equal to negative work elect from infinity to R. Okay, so now we need to expand this equation to find the equation for U. We want to expand this work done over here. So what you have learned from last semester is that if you are finding work done, W, work done can be found using two methods in our syllabus. Okay, so if your force is constant, you can find work done very easily just by using W is equals to F dot S, which should be equals to Fs cos theta. A very straightforward equation. Okay, but today, if your force is not constant, if F is not constant, what happens is you might need to rely on the area graph. This is what we learned from last semester. You look at the area under the force displacement graph, that is where you can find the work done. Okay, but we know that displacement S in this particular chapter, we already changed the distance to become R, right? So right now, this is no longer Fs, it's Fr graph. Okay, and I hope you all can see a bit of hint of where I'm going to go here, because area under the graph, actually, look at area under the graph here actually means integration. Because we know that if you want to find the gradient of a graph, we use differentiation, right? dy dx is the gradient of a y-axis graph. So if you want to determine the area under the graph, you are forced to use integration. That's a technique you need to know. Okay, so our graph over here is a force against distance graph. Okay, so your Q is initially here, this is your Q, and your charge Q is somewhere initially very far away. Okay, so let's say this is infinity. Okay, so the charge is going to move towards a certain point, which is now having a distance R. Okay, Q initially was here, then later Q will move towards here. Okay, let me tidy up the stiff stuff over here. Q will move towards here. Okay, so we know from our discussion just now, the distance between Q and Q final is R. Okay, and the distance initially over here was infinity. Okay, you know that the force that we are going to study here, force electric, right? So electric force follows KQQ over R squared. F is equals to KQQ modulus. And because it's an R squared graph, if you refer to your function chapter in maths, you know that the graph will look something like this. It's near infinity, but here as you approach infinity, you approach 0. Okay, let's say here is infinity, then it reaches 0. So what we need to find now is we need to find the area under the graph from here, because here is infinity, to here, because this is distance R. So this is the area under the graph that we are going to study. Okay, so we are going to find this thing using integration. We know the equation is fkqq over r squared. So what are we going to do? We are going to change it into an integration sign. So this is integration. We are integrating the function. The function is kqq over r squared. We're not going to put in the modulus. Then this is against the x-axis dr. Okay, and we are going to integrate from an initial r, which is infinity. Initially the r is infinity. Finally the r is r. So we are going to integrate from infinity to r. This is the equation. Okay, so I'm going to use a bit of integration. I hope we have learned about it. But the first step is we always bring out things that are constant. Throughout this process over here, what is changing is the distance between q and q. Initially it was infinity, now it is r. So the r is changing, so we should definitely leave the r inside this integration. But k is a constant, and q here never get changed. It's still the same charge over here, it's still the same charge over here. So k, q, q are actually all constants. So we can bring it out from the differentiation bracket. So it becomes k, q, q on the outside. And we are left with 1 over r squared to be integrated over here. Okay, you can explore it by your own, but if you refer to your mathematics classes, I believe you can integrate this quite confidently and you get this is negative 1 over r. Okay, it's nothing to do with natural log. You're not getting ln r as a result. Ln r is 1 over r, integrate become ln r. But this is 1 over r squared. If you do it slowly, the negative 2 plus 1 divided by negative 2 plus 1, and you go expand it, it's negative 1 over r. Okay, so we keep the upper limit, lower limit over here. So right now, if I expand the equation, this should be negative 1 over r minus negative 1 over infinity. Okay, 1 over infinity will be equals to 0, so we can just ignore everything on the back. So we can see there's a negative sign and a negative sign over here, so they will combine to become a positive sign. So at the end of the derivation, you see that the derivation becomes KQQ over R. And this is the equation for electric potential energy. So just now we asked about what is the electric potential energy stored here? Well, you can just figure it out by using the equation that we have just derived. So if you want to find it out, you can say U is just equals U and between Q and Q is just between K, Q, Q divided by the distance between Q, Q. Okay, so if you go calculate this thing, you get the answer to represent the electric potential energy being stored here. Okay, so just a little reminder for this equation. There's no modulus for Q and Q. Okay, So we're not adding a modulus, unlike electric force, unlike electric field. Electric force, electric field, all the charge we put modulus. But when we talk about energy, all the charge we don't put modulus. So you have to include the sign in your substitution. So include sign in substitution. Okay, so this is how we can manage to obtain the equation that helps us to know in between a pair of charge what is the electric potential energy being stored in between them. Okay, so knowing this thing already, we are going to progress a little bit further to end up our discussion on electric potential energy. So the last thing I want to discuss for electric potential energy is, what if we study the electric potential energy of a system with more than two charges? Okay, so all this while our discussion has always been just a pair of charge only. But what if we have more than two charges? How should we talk about the electric potential energy for these cases here? Okay, so I'm going to give a very general example. So let's say today I have charge 1, Q1. I'm not going to discuss with you whether it's positive or negative. I'm going to have another charge Q2. I'm going to have another charge Q3. So let's say this is a 3-charge situation over here. We know that in between every pair of charge, okay, so how many pairs do we have? Q1, Q2, Q2, Q3, and Q1, Q3. We know that in between every pair of charge, based on our understanding, we can think of it as if there's a pair, there's a spring in between them. So I think at this point, it would be great if we can assume there is a spring in between each pair of charges. Okay, so this pair, in between them, there will be a spring, so we can call this electric potential energy to be equal to U between 1 and 2. So charge 1 and charge 2. And you can easily find the value over here by doing KQ1, Q2 divided by R plus 2. Okay, following up over here on this side, you have another spring over here. So this one is between charge 2 and charge 3. So we can call this as U23, in which U23 can be obtained by using K. Then you have charge 2, you have charge 3, Q2, Q3 divided by R23. Okay, lastly, we don't forget about the last pair as well. There's the last pair over here. This last pair over here, we can also expect there's a pair of there's spring in between them. You can imagine there's spring in between them. But this time, this energy being stored over here in between Q1 and Q3 is called U13, and it's K Q1, Q3 over R13. Okay, so there are 3 springs being involved over here. Okay, so there's actually a few types of electric potential energy that a question can ask for. So let's say they can say, what is the electric potential energy of charge 1? It's a U1 of charge 1, okay? So it's actually not really true to call it of charge 1, but in our syllabus we usually see of Q1, okay? Or it sometimes can be said as, the correct way of saying it is associated with Q1. Q1 is a big Q, right? Okay, if the question asks what is the electric potential energy of Q1, or they say what is electric potential energy associated with Q1, that means by they want to know all the potential energy that is related to Q1. We can say there are 3 springs over here. All springs here store some amount of energy. But related to Q1, there's only 2 springs that are related to Q1. There is the spring between Q1 and Q2, and the spring between Q1 and Q3. Only these 2 springs are connected to Q1. This green spring over here is actually not connected to Q1. So this U23 here will be left out when we are calculating U1. We only sum up all the energies for the spring that connects to Q1. So we can therefore say that, a bit of space, we can therefore say that this U1 over here can be equals to U12, adding it up with U13. So if you want to further expand it, you can equals to KQ1 Q2 over R12 and plus KQ1 Q3 over R13. Okay, so let me expand it. This KQ1 Q2 over R12. This one is KQ1 Q3 over R13. Okay, so this is how you can obtain the electric potential energy of Q1 or electric potential energy associated with Q1. The better way is to use associate because as you can see, this spring here stores energy not only on the Q1. This spring here stores energy in between Q1 and Q2. So this energy here is not totally owned by Q1. It's actually shared between Q1, Q2 and shared between Q1 and Q3. Okay, so that's why this way is actually more appropriate, but our syllabus always use offer. Okay, continue on that, you can find the electric potential energy of U2. I'm not going to write very long, but U2 we actually look at the two springs connected to it, charge 2 only. So this one will be U12, adding it up with U23. Okay, whereas if you want to find U3 associated with charge 3, then there's U13 and U23. Okay, and the most complicated kind of question is what if they ask what is the electric potential energy of the system, or what is the total electric potential energy? Okay, that is just equals to adding up all the springs that you can find in this particular diagram. So it will be equals to U12 plus U13 plus U23. So that is how you obtain U system or U total. So there are 4 points here which you should take precaution now. Whether the question asks for electric potential energy associated to a single charge or they ask for the whole electric potential energy. So these are things that you need to be careful of when you are solving the questions. Okay, so I think that's where I would like to put a stop. I've already successfully do it my way in explaining how work done can be related to change of electric potential energy. And I already tell you how you can determine your electric potential energy. If it's a pair of charge, you can just find the electric potential energy using this equation. If there's more than a pair of charge, you need to see whether the question asks for the electric potential energy of a single charge or they ask for the total electric potential energy of the system. So if they ask for a single charge, only add up potential energy associated to that charge, only add up springs that are connected to that charge. If they ask for the electric potential energy of the system, you add up every single spring that you see in this particular diagram. So this will help you determine the electric potential energy if there's more than 2 charges. So I'm done with electric potential energy. In the next session, I'm going to relate to the next quantity, which is electric potential. And to discuss electric potential, I'll actually bring out something from section 1, which is electric field. Because I think electric field and electric potential are actually very, very similar. So I'll bring them to be compared side by side for you to have a rough idea what is electric potential. Okay, so that's it for this particular part of the explanation.